Okay, what I've got here is in our environment, and I've ran all of the code through the end of video 2. And you can see here at the end of video 2, we verified that we had the correct proportions in our training set and our test set for our class labels between ham and spam. Okay. We then also talked quite a bit about representation, and we're going to continue right on where we left off with those slides, where we're going to start taking a look at a few pieces of selected data out of the training set, so we can get some idea of what these considerations mean in practice. Okay, so here I'm going to go ahead and access the 21st entry in the training data set. And you can see here that it says, I'm back and we're packing the car now. I'll let you know if there's room. But most importantly, notice this right here. So this is an HTML escaped ampersand, right? Essentially these 5 characters should render just that on the screen. Now, this is often the case when you're working with text analytics, is that stuff that you see rendered in a particular way isn't exactly how it will be represented in the raw textual data that you will get. This is a perfect example. This is an escape sequence that actually denotes, hey, place this on the screen, but this is what you'll actually get. So one of the things that you'll need to decide as a data scientist working with text is, how are you going to handle that? So one viable approach is just to do a bulk search and replace. You can literally go through all of your code and say, look, if I see this particular sequence, go ahead and replace it automatically with that. Or alternatively, you could replace this whole escape sequence with the word and. That would work as well. Or you can do some various other types of techniques as well. You could strip off just the ampersand and the semicolon, leave the word amp in there. Now, unfortunately, amp is an actual word, so that your mileage may vary depending on the domain that you're working in, of which strategy is the best. Because this tutorial is very introductory, we're just going to go ahead and blast away these symbols, the ampersand and the semicolon. We'll leave the word amp in here, and we will assume, as we described earlier when we talked about stemming, we will assume that if the word amp, which is left over, shows up in any of the RSMS text messages, we'll be able to actually differentiate between amp as being a proxy for the word and, the ampersand, the symbol ampersand, or the word and, versus an SMS text related to maybe electrical domain, where amp is actually a measurement of the electrical domain. It's extremely unlikely, it's possible, but it's extremely unlikely that our SMS text data would have something from the electrical domain in there. So it may end up being okay for us just to use amp as a proxy for the word and. But like I said, you could certainly just do a wholesale search and replace. And a very viable strategy would be is just take this and replace it with the word and then you'd be good to go. Okay, so that's one example of the considerations that we talked about at the end of video 2. So moving on, we're going to go ahead and also take a look at a next piece of data here. And you can see that right there. A gram usually runs like ampersand LT semicolon hashtag ampersand GT semicolon. So these are essentially the symbols for less than and greater than. And once again, the same idea applies. The same idea applies. How do we actually want to treat this? If we replace these with the actual symbols less than and then greater than, they would likely get stripped out, because as we talked about at the end of video 2, we tend to strip out symbols. We typically only care about words. So we tend to strip out symbols and punctuation and numbers, digits, all that kind of stuff. So you may have to decide what you want to do here. For example, you could just leave LT. That would actually probably work out okay, because LT would be essentially the moral equivalent of you maybe doing a search and replace on this altogether and replacing this with the word less space than, or the two words less and than. Same thing here. Because eventually what will happen is the machine learning model will pick up, if there's any signal in the textual data, it will pick up that LT essentially is a proxy for the concept of the less than symbol. Now also, we also need, as we mentioned in video 2, we got hashtags here. Now normally you pull them out. However, in this day and age of social media, you may want to decide, look, you know what, hashtags are actually kind of important. Just like @ symbols may be potentially important. The example we used last time, which I'll repeat, is if you were doing sentiment analysis, sentiment classification on Twitter tweets, you would care very much about hashtags and @ symbols. But again, because this is a rather simplistic tutorial, we're going to go ahead and omit symbols. So we'll get rid of this, we'll get rid of this, we'll get rid of the hashtag here, the and all that. And essentially this will boil down to LT and GT. LT and GT. Okay. And lastly, another example to take a look at is a URL. Your credits have been topped up for http www.bubbletext.com. So this is an example of a URL. As you might imagine, URLs are extremely common in textual data these days, and it's something you really need to concern yourself with, because you can essentially decompose this in a number of ways. For example, you could get rid of these two symbols and just have HTTP and then have www.bubbletext.com. You could segment out the .com. You could segment out the bubble text. You could do all kinds of things with URLs. And as we talked about, Quanteda as well as other packages and functions give you a wide range of functionality in terms of working with text, and especially things like special characters and hyphens and URLs and Twitter data, you name it. So you'll have to decide. Again, since this is an introductory tutorial, we're going to go ahead and take the tactic of, we'll probably just split this out as HTTP and then probably just use bubbletext.com separately. And what will end up happening if we do this consistently is eventually the machine learning model, if there's signal in the data, eventually the machine learning model will learn that HTTP is the proxy for some sort of website. Because more than likely, given our relatively small sample size, while it's possible, it's probably unlikely that we're going to have a lot of duplicate URLs themselves. So for example, bubbletext.com itself probably won't be highly predictive, but maybe there's a chance that, for example, the machine learning model may learn, hey, generally speaking, 70-80% of texts that have HTTP in them are spam, so that may become a powerful feature for us. So we'll have to take a look and see what happens as we go along in the video series along those lines. Okay, so there you have it. Just a few examples of the considerations that we talked about at end of video 2 regarding what you need to do for pre-processing your text data, the kinds of things you need to be on the lookout for. All right, moving on. Okay, so let's go ahead and actually load up the Quanteda package here. And I hope I'm pronouncing that correctly. Maybe it's Quanteda, I'm not sure. But I'll just call it Quanteda. Okay, so we're going to load up the library here, and then we'll run the help file on it. And you can see here, you get quantitative analysis of textual data. That's what Quanteda is. And as usual, you want to click the second link over here in the help file, and you get this nice getting started guide. If you pull up the HTML, a lot of goodness here. Quanteda is a super, super awesome package to work with. It's become my de facto standard package to work with now in R, supplanting some of the ones I used to use, like the TM package, the text mining package, OpenNLP, and things like that. There's a lot of goodness in Quanteda, a lot of goodness, as we'll see in a second. Okay. So first up, we're going to go ahead and leverage the Quanteda package's tokens function. So as always, tokens, there we go. Tokenize a set of texts. And as you know from video number 2, tokenization is just the process of breaking up a text document into chunks. And I won't drain this help file because, as you can see, there's a lot of goodness involved here. There's a lot of functionality, a lot of parameters, a lot of things that you can do. I'll show you an example here, and this is again under the 80-20 rule. It's 20% that's going to be helpful to you 80% of the time. So first up, we're going to ask quanteda to tokenize our text column on our training data. Hey, quanteda, go through all 3,901 observations, all 3,901, SMS text messages, and tokenize each one. And what I would like you to tokenize are the words. Now, there are different options available to you. For example, you can do individual characters. Super awesome, super interesting, but generally speaking, most of the time you're going to be using words, right? Essentially anything denoted by space in English language, right? So we want you to tokenize all of these texts into words. Now, per our conversation, per our slides in video number 2, we also have the ability to control at the fine-grained level how the tokenization process is actually executed. For example, we're going to go ahead and tell the tokens function to remove digits. Anything with a digit in it. A 0, a 1, 2, 333,413, whatever. If it's a number in terms of digits, remove it. Now later on in the video series, we'll probably swing back around and take a look at maybe engineering some features based on numbers. But for right now, we'll just go ahead and take them out and see how far we can get. Next up is we're going to go ahead and tell the tokens function to remove punctuation, commas, exclamation points, question marks, you name it. Please remove the punctuation. I don't want that. All I want are the words. I don't want the digits and I don't want the punctuation. I just want the words. Similarly, also, please tokens remove any symbols. So hashtags, @ symbols, ampersands, you name it, slashes, all that gone, $signs, all of them gone. We're going to remove the symbols as well. And lastly, anything that's hyphenated, we're going to remove the hyphens, essentially turn it into a space. So for example, if somebody had a some sort of hyphenated word, I'm trying to think of one right now, long term, right? So they had long dash term, long hyphen term. This would actually translate into the word long and the word term separated by a space. It would get rid of the hyphen. It would get rid of the dash in the middle. Okay. So we can ask quanteda to run this and it'll tokenize all of our text for us with these particular caveats in place. Get rid of the numbers, get rid of the punctuation, get rid of the symbols, and get rid of the hyphens. Okay. Now if I run this line of code, I get back a large matrix here. Large DFM sparse here. Large DFM sparse. This is a particular object associated with the quanteda package, but it's actually pretty easy to work with. So for example, if we wanted to look at just the tokens of the 357th entry, and I picked this one for a reason, by the way, just so you know. If I run this, it'll actually spit out the tokens. Now you'll notice that this 357 corresponds to the text with the URL that we talked about earlier. So what we're going to do is we're going to run through a series of steps. This is known oftentimes as a pipeline. We're going to go through a text analytics data pre-processing pipeline here, step by step. And what we'll do each step of the way is run this same line of code over and over again, and we'll see how the raw text transforms over time. Right? So just to really make that pop. So here was the original text, right here. And here it is tokenized, right? Which makes sense, right? Essentially it's just the words. But notice that we have HTTP and www.bubbletext.com as two separate things, like we were talking about before. This will allow the machine learning model to pick up on any signal if HTTP tends to be indicative of something, essentially ham or spam. Okay, so first step in the pipeline, we tokenize, no problem. Okay, next step, not surprisingly, as we talked about before and at the end of video 2, is we're going to lowercase everything. We're going to lowercase everything. And that's usually because, once again, our bag of words models tend to work very, very well without understanding things like capitalization, formal names of things, they tend to work really well without them. So generally speaking, we just lowercase everything to make sure that we have all of the words are into a single column. Because last thing we would want is two columns, one with your with a capital Y, and then another one, another column in our data frame for the word your without Y capitalized, lowercase y. So that would be kind of silly. So we just lowercase everything. So per our process, tokens underscore to lower does exactly what you would think. Convert the case of tokens. So you tokenize first using quanteda, and then you can do various transformations on the tokens that you've produced. We're going to transform our tokens to be lowercase. So if we run these two lines of code, you can see here now the word your has been lowercase. And since everything else was already lowercase, it looks exactly the same. So this is two very common steps, almost de facto standard in a text analytics pre-processing data pipeline. Tokenize your texts, lowercase them. Okay, next up on the hit parade, stop words. Stop words. So stop words are, as we talked about in video 2, they are common words that are used in language that are typically used for grammatical sugar. They make the language flow, they make the language stream a little bit more streamlined, but in general, they don't add anything in terms of semantics, in terms of meaning, in terms of predictive power. So in the English language, the classic example is the word the. Typically, you want to remove stop words. Now, there's a note here in the comments which I should mention, which is quanteda, as with many text analytics libraries, whether in R or Python or Java or you name it, will have predefined stop word lists. Now, depending on what problem domain you're working in, these stop word lists may be okay. They may have all the words on them and you say, fine, great, take them all out, I don't care. But sometimes you may actually care, and they may have more words in their list than you want actually taken out. So it's important to understand what is in the stop words list so that you can understand what the impact of that is in particular. So in quanteda, you can get the English stop words that are included by quanteda by default by using the stop words function. So let's pull up the stop words function. And we can access the built-in stop words. So for example, if we just ran this line of code here, you'll see here is the list of all of the stop words included by default in quanteda. Basically, if quanteda finds the word shan't, not likely, but possible, if it finds the word shan't, it's going to pull it out. It's going to remove that token because we don't want it anymore. So you go through this list, see if it works for you, and just be aware in general, anytime you're working with these libraries, make sure that the default lists of stop words will work for your particular problem domain. Okay, moving on. Tokens select. Let's look up that function because this is the function we're going to call. Select or remove tokens from a token object. Okay, cool. Makes some sense. Now this full line of code, this full function call makes a lot more sense now. Quanteda, please select some tokens for me. Select from this particular object of tokens. In particular, I'm interested in these words here, the stop words, and I would like you to remove them. So I'm just going to go ahead and run this line of code again just to set our output up again. And if I run these two lines of code, now you'll see that before we had all of our stop words in here, right? We had all of our stop words in here. We had your and been and have and all that and up and all that sort of thing. And you'll notice now we have a much smaller list of words. We removed the stop words because your probably isn't predictive. Because remember, the reason why it's not going to be predictive is because the bag of words model is positionally ignorant. So words like your and have and been kind of need position for them to actually have any sort of significance. And because the bag of words model by default basically messes with the token order, the word order, these words have a lot less predictive power than they would normally have. So we just remove them. And then what we get essentially is these remaining terms. tokens. Credits, topped, renewal, HTTP, pin, bubbletext.com, and TGXXRZ, whatever that means. Okay. Now, lastly, we're going to go ahead and we're going to stem. Now, if you remember from video number 2, stemming is a super important process. Stemming is the way we take words that are very similar and we collapse them down into essentially a single term, a single column in our term frequency matrix. For example, we use the words ran, run, runs, and running as a particular example. What we would like is a process to say, okay, look, ran, runs, and running. Anytime you see one of those 3 words, change it into just the word run. And that way we essentially get this collapsing effect. Instead of having 4 columns for ran, run, runs, and running, we have just one single column that embodies the idea behind run. And in the example we used is in one context, the idea of run is essentially a human being moving as fast as they can under their own power. And we said, well, there could be other contexts as well, but that's okay because we can rely in the bag of words model on the other words in the document to provide context. And the example we used was computer systems, IT. If ran and runs and running were all related to computer systems, be okay. We could still collapse all of that down to the same single column. And other words like hard drive, and CPU, and disk, and network, and RAM, those sorts of things would then provide context to the model, to the machine learning model, that run in this case was not about a human being. Run was essentially about a computer system. Okay, so let's go ahead and look up the function tokens word stem. Okay, stem the terms in an object. Cool, right? Exactly what you would expect. So we're going to go ahead and use this function. Here's our tokens, and we're going to say, look, it's the English language that we're using. It's the English language that we're using. Now, if we run these 2 lines of code, you'll notice credits now became credit. Topped now became top. HTTP remains the same. Pin remains the same. Renewal became renew. And then these 2, the bubbletext.com and TGXXRZ, stayed the same. Now notice something really important here. Let's take a look at topped. Topped, tops, topping. These all have the same general concept of top. Notice how they get collapsed down. Same thing. Renewal, renewing, renews. All can get collapsed down to renew. Credits, credited, creditor, could all be collapsed down to credit. See how that works? That's stemming in action for you. So stemming is super, super powerful. And essentially what we've just walked through is the prototypical, almost de facto standard text analytics data pre-processing pipeline. Tokenize, lowercase, remove numbers, remove punctuation, remove hyphens and symbols, lowercase, get rid of stop words, and stem. Quintessential data pipeline. Okay. Now, of course, as I've mentioned several times before in previous videos, broad space text analytics is. You could certainly do other types of things as well, but this is, again, the 80-20 rule. This is 20% of the stuff that'll get you useful results 80% of the time. Classic pipeline here. Okay, so now that we've got our data pre-processed, let's go ahead and create our first bag of words model. Quanteda has a function called DFM. Oops, you gotta spell it right, Dave. So, DFM, create a document feature matrix or a document frequency matrix, depending on how you want to think about it. But DFM is a function that will essentially take tokens, and as we'll see later, it can also take in just textual features as well. But it'll take in tokens, it'll take in our pre-processed tokens, and create for us a DFM, a matrix. Now, since we've already done a bunch of pre-processing, we don't need to set a lot of parameters on the DFM function. We just say, okay, DFM, please process our training tokens. You don't have to lowercase them because I've already done that. And you can go ahead and remove the stop words. This essentially is redundant. So we could just get rid of that actually because we've already removed the stop words up here. So we don't need to do that. Save us a little bit of processing time. And if we run that line of code, we get back an object. Now, the object itself isn't super useful, but Quanteda provides, some functions that are actually quite worthwhile for us. There's a function called as.matrix. There's also one called as.data.frame. And these are functions you can use on DFMs that you return back, document frequency matrices that you return back from this function. And you can convert them into representations that are a little easier for you to work with. So for example, if I make this a matrix, it becomes just a standard R matrix, which I can then view in the spreadsheet view. So I'm going to run those 2 lines of code here. And what you're seeing is essentially the first 20 rows, and the first 100 columns of our DFM. And you can see here, go and Jurong and point and crazy. That looks like probably been stemmed, right? C-R-A-Z-I. Avail, Bugie, maybe? Great, World, Buffet, you name it, right? There's a whole bunch of columns here. And these are all columns for our distinct individual tokens for all of our terms. And you can see here counts. Like for example, promise, which I'm assuming this is the stemmed version of the word promise. Notice that it's a little bit mangled. There was 2, count of 2 in this particular SMS text message. Notice that most of the time you're going to see zeros. Most of the time you're going to see zeros. Okay, so there it is. We got a DFM. Great. Now, this is something that we're going to be talking quite a bit about in this video series. Check this out. So, you'll notice that our training data was originally 3,901 observations of 3 variables. We now have a feature matrix in our bag of words model that's much, much bigger. Notice that it's still 3,901 observations, right? Because the number of text messages does not change. But what does change is the number of columns. We now have 5,743 columns. So it's 3,901 rows deep and 5,743 columns wide. And as we know from this particular representation, most of the time, this is going to be really, really wide. This is only 100 columns wide. This is going to be more than 5,700 columns wide. And most of the time, most of the entries are going to be 0. So this is super interesting thing to remember. Another challenge of text analytics is that it creates your data, the size of data that you deal with explodes very, very quickly. Very, very quickly. I mean, we're only using SMS text messages here, and we're only using 3,901 of them. And text messages, generally speaking, are fairly small. But notice how many columns we get. Now, imagine if you were doing this on 3,901 Word documents. This would be 20,000, 30,000, 40,000 maybe, depending. Your feature space explodes dramatically. The dimensionality increases dramatically. If you're familiar with the term, text analytics very, very much suffers from the curse of dimensionality. That's one problem. The other problem is this idea that we see here, which is most of the time our matrices are going to be very, very large. They're going to be relatively deep because we'll have lots of documents, but they're going to be very, very wide. And most of the time the cells are going to be essentially 0. They're going to be empty. So this is a sparsity problem. So what we have is not only do we have a large dimensionality problem, a cursive dimensionality problem, but we also have a sparsity problem. And we'll address that later with techniques like feature extraction. But these are things to know. Your data gets big in text analytics very, very fast. Very, very fast. Okay. And we can give you some example here. We're just going to take a look at the first 50 column names here. And some of these you'll recognize from the spreadsheet view, but I just wanted to print them out to the console to make them pop a little bit. Go and Jurong and point. Notice crazy. This is safe to assume that this is a result of stemming. Avail, also safe to assume the result of stemming. Already, look at this. Look how it changed the Y to an I. Also safe to assume the result of stemming. So notice that even though stemming was super useful in collapsing down the number of columns we need by standardizing our words, we still have a lot of columns here, 5,743 columns. Okay, so we're over time, so I'll go ahead and stop there. There you have it, a fully functioning standard, de facto standard text analytics data processing pipeline, data pre-processing pipeline. Okay, next time we'll actually build our first model over our feature matrix that we've just created. So if you like what we're doing, please subscribe to the Data Science Dojo YouTube channel. We'll be producing new content on a regular basis. Also, if you like what we're doing in general here at Data Science Dojo, feel free to follow us on social media. And lastly, I hope to see you in one of our upcoming Data Science Dojo boot camps. Until next time, this is Dave Langer, your host, and I wish you very happy data sleuthing.